Why doesn't our cell membrane fall apart when it's too hot? Or why doesn't our cell membrane freeze when it gets too cold? Well, our cell membrane actually has a very unique property called membrane fluidity. Now, a lot of different factors can affect membrane fluidity, but the three most important ones that we're going to focus on today are number 1, temperature, number 2, cholesterol, and number 3, which is whether we have unsaturated or saturated fatty acids. Now, just to quickly remind us, the building blocks of a cell membrane are what we call phospholipids. And it looks like this. There's a phosphate head group that's represented by a circle and 2 fatty acid chains, kind of like strings hanging below. And in this video, we're actually really going to focus in on the impact of phospholipids in our cell membrane. So the first thing we're going to start off with is temperature. We have low temperature, and obviously we have high temperature. So let's pretend that our cell membrane is only made up of phospholipids. What do you think our cell membrane is going to look like at low temperatures? Since the temperature is low, our phospholipids are actually going to start clustering together really closely, kind of like that. And the reason why is because these phospholipids are at the low temperature, which means they don't have a lot of energy to move around a lot. So they're going to huddle really close together. At extremely low temperatures, we actually call this a crystallized state. And since they're huddled so close together and they don't have a lot of energy to move around, the fluidity is actually pretty low. So as the temperature decreases, the fluidity of the cell membrane also decreases. What happens at high temperatures? Well, at high temperatures, our phospholipids have a little more energy. So they're actually going to move around a little bit more and cause themselves to have more of a distance between each other, kind of like that. So you'll notice that the distance between phospholipids is now much greater than what it was over here, which at low temperatures, which was very, very small. So this increased distance allows our fluidity to increase because there's much more room for the cell membrane to move around. So as the temperature increases, our membrane fluidity also increases. What happens when we add cholesterol? Well, at low temperatures, our phospholipids still tend to cluster pretty closely together. But occasionally, something really interesting happens, which is when cholesterol actually inserts itself between the phospholipids, like this. And it doesn't do this for every single phospholipid, but it'll occasionally insert itself into the membrane. The same goes for the phospholipids that are underneath. And you'll notice that the membrane doesn't always have to line up, in the sense that the phospholipids can actually be in the same place as the ones above, or in a slightly different place. In some membranes, there's more cholesterol, and in others, there is less. But the presence of cholesterol itself does something really unique. And what that is it actually increases the distance between some of the phospholipids. And like we've talked about for the high temperatures, as the distance between the phospholipids increases, the fluidity can also increase. What happens at high temperatures with cholesterol? At high temperatures, our phospholipids are already pretty far apart, just like the above picture. But just like before, the cholesterol will insert itself into the membrane at random places. And what this will actually do is it will cause the phospholipids to pull themselves closer together because they kind of want to attach to that cholesterol. So now there's more stuff inserted throughout the membrane, and so the molecules in the membrane are now closer together. So the fluidity actually decreases. So cholesterol is actually really interesting because at low temperatures, the fluidity will increase, and at high temperatures, the fluidity will decrease. You can kind of think about cholesterol like a buffer, kind of like in chemistry. It allows our cell membrane to remain at a fairly stable and normal level of fluidity. When the temperature gets too low, the fluidity will increase a little, and when the temperature gets too high, the fluidity will decrease. So moving on to our third one, which is the presence of saturated or versus unsaturated fats, we're going to go ahead and make a new canvas to give ourselves a little bit of room. So in number 3, we're comparing the presence of saturated versus unsaturated fats. And when we're talking about saturated versus unsaturated, we're talking about the fatty acid chains that are hanging below our phosphate head group. So just to remind us from chemistry, a saturated fatty acid can be represented like this, where every angle or pointy end is a carbon. In the case of an unsaturated fatty acid, it can look pretty different, because an unsaturated fatty acid means that we have some double bonds. So let's say we have 2 double bonds like that. By themselves, it doesn't seem to be anything special. Granted, they look different. But how would these interact with multiple fatty acids next to them? So in the case of a saturated one, and in the case of an unsaturated one, our molecule will still have some double bonds. And what's really unique is you'll notice that in the saturated fatty acid, these two fatty acid chains stack together really neatly, kind of like Legos. But in our unsaturated fatty acid, these two don't really stack together that neatly. How will this affect our membrane fluidity? Well, for the sake of this particular explanation, we're going to draw the saturated fatty acid chains as straight lines like this. And just because we're trying to represent the fact that these straight lines stack together really well. So what's going to happen is they'll stack pretty closely together, and so will the ones underneath. And since the distances between the molecules is pretty small, our fluidity is actually pretty low. So what do you think will happen with our unsaturated fatty acids? Well, you'll notice that there's a little bit of a bend now in these fatty acid chains. So I'm actually going to represent the phospholipid with a little bend in it. And these might occur at different places, or they might have both of them being bent. But you'll notice that I'm unable to draw these phospholipids as closely together. There becomes more distance between these phospholipids because of this unsaturated bend in our phospholipids. So since there's more distance between our phospholipids, the fluidity increases. So just to quickly sum up, today we learned the three factors that can affect membrane fluidity. The first being temperature. As temperature increases, fluidity also increases. The second is cholesterol. And cholesterol acts as a buffer, increasing fluidity at low temperatures and decreasing fluidity at high temperatures. And the last are unsaturated fatty acids in our phospholipid. When we increase the amount of unsaturated fatty acids in our cell membrane, the fluidity also increases.